Hi, I'm gonna start talking about our project 2, and I chose to do it on optics. So I think where to begin best with optics would have to be with the discussion of lenses, and there are two types. So the two types that we have are the convex and the concave. See there. Now, they have two distinct shapes, and these shapes can tell a lot about what like the roles are. So for the convex, it's thicker on the outsides and thinner on the insides compared to the other way around. Let's see, like this. So as you can see, concave is thicker in the middle and convex is thinner in the middle, and this affects how light will go through it. So concave is a focusing point. That's where they all meet, and convex they don't meet. What we can see here is if we draw the rays of light, so if it goes straight, it'll go straight in. If it goes like this, it'll bounce out straight in there. It bounces out there. So what we can see is how it disperses all the light, and that there's not one central focus point. And then we see the opposite in a concave. In concave, we see a convergence of light to a central focal point where all light meets. Now, what does this allow us to do, or what are some equations that go with this? So I think one of the more main equations that we can go over is 1 over f equals 1 over d plus 1 over di. Basically what this is saying is that the focal point is equal to, well, 1 over the focal point is equal to 1 over the distance to the object plus 1 over distance to the image. And here we can see a whole manner of other things. We also have magnification is equal to the distance to the image over the distance to the object minus. And that can tell us the magnification, or if the image was increased in size, decreased, and just overall what we can kind of picture from like the formulas and stuff like that. So I prepared a little practice question, and I'll write down kind of all we're using. So it's given that the height of the object, or HO, is equal to 10 centimeters. The distance to the object is 15 centimeters. The focal is 5 centimeters. And we're looking for the distance to the image. We're also going to talk about a couple other things, but this is what we're mainly going to do here. So what the equation we can obviously use here first that fills out all the principles that we're looking for, because again we're looking for the distance to the image, is the first equation. In the first equation we can see that 1 over f, or 1 over 5 centimeters, is equal to 1 over 15 plus 1 over di. So then what we can do here is, using some algebra, we can multiply both sides by 15 di and multiply the other side by 15 di. And this will get rid of all the fractions and then allow us to use the principles. So it would be 15 over 5 di, or just 3 di. So I'll just get rid of that and just write 3 di is equal to, so when we do it this way, it would be 15, so it would just be di. And then this time the di's would cancel. It would just be 15 So when we subtract di to both sides, we're left with 2 di is equal to 15. So di is equal to 15 divided by 2. And that's our answer, of course, in centimeters. So what does this allow? Like, what can we get from the fact that we have the 3 di is equal to di plus 15? We can actually tell whether or not this image is real or virtual. So in this case, because di is a positive number, we know that it is real. But if di, say, would be like a negative value, or we got something negative from it, we would have a virtual image. So something else we can do with this equation, now that we have the distance to the image, is find the magnification at this point. So to do that, we do m is equal to negative di over do. So this ends up being 15 over 2 divided by 15. So it'll just be half. Because what we end up seeing is that it's 15 over 2 times 1 over 15, just be 1/2. So if the m value is equal to 1/2, so the magnification on this is 1/2. So what does this tell us? Now we know, because of other principles, that if the m value is, if the absolute value of m is greater than 1, it's enlarged. If the absolute value is less than 1, it is reduced, and if it is equal to, it is the same size. So what we see is that the image is actually half that, because the absolute value of 1/2 is less than the value of 1. So the number is overall reduced in this problem. So now I'm going to pause it here, and then I'm going to go to a different aspect of this. Okay, so some of the real-world examples of this, real-world, is microscopes, telescopes, and glasses. This can be anything from like polarized lenses to actual just like reading glasses or just anything, any type of glasses. Now I'm going to start off with telescopes. And telescopes are actually a combination of 2 different optical principles. So it has both mirrors and lenses that operate with each other to make a more perfect apparatus, basically. So what kind of happens in a more basic design is that you'll get light that gets filtered into the tube from both sides, and then it'll hit a mirror on the bottom that is curved towards a certain angle. That'll bounce the light to a singular point here where it is viewable to an actual observer. So that's how we can use mirrors and lenses together, by the principle of just bending light so that it is able to be seen. And in this case, the telescopes allow us to see like very far off planets and stars and stuff like that in our solar system. So that's how it's done. It's the light that's captured and bent to a singular image so that it magnifies it, so we can actually see what's going on there as we see the light enters and then gets reflected to another here, and then out to an actual viewing point for people so that they can understand what's going on. They can actually see the outside world. Another one that we have is glasses. Now we can see that the glasses have both a lens property, so they can help focus light and make people see better who have like far and nearsighted vision. But we can also see for polarization. Now polarization is given in the equation that I is equal to I naught cos squared theta. And this is basically just telling us that the intensity is equal to the original intensity times the cosine squared of theta. And The way that theta works is by rotating polarizers that only allow a certain type of wavelength through, or a certain degree of light in. So what it ends up kind of looking like is that if we were given like an axis here, we would have kind of like a little disc with a slit in it that only allow that kind of light. But unpolarized light is considerably random, so it comes in from basically all sides. But afterwards, the only light that's able to go through this would be like that. It would fit the slit there. So with this, there's actually two kind of principles. So you can actually add polarizers together that would decrease light completely, making it zero. And what would that look like exactly? That would be where one polarizer, let's say, is horizontally and the other is vertically. And there we would get a light or a theta that is equal to 90 degrees. And what do we know about a cosine of 90? It's that if cosine is a cosine of 90 would be equal to 0, so 0 squared would be 0. So that means that there is no light being able to pass through, and we can see that because this slit is entirely horizontal and this is entirely vertical, so there's just no way that anything can go through it. But let's say we can actually increase light by adding polarizers, and how we would do this is in the same example. Let me draw this a little better. In the same example, we have these two, and if we add one in the middle, say at like a 45 degree, we actually add a change on the actual phasing, or in theta, that would be 45 degrees between them both. And then that changes the overall equation, and it allows light in. So adding polarizers can actually increase the amount of light through an object. And at the same time, adding polarizers can also decrease depending on how they're arranged. And we can also use this to see the angles based on like their intensity. 1 second. And for this, I have an equation for it. Or we'll use the same equation, but basically the question is, so only it's at 50% of the amount of intensity is passing through, like the light is only 50% going through the whole thing. So how would we do that with I equals I naught cos squared theta? So what we're trying to find here is where at 50% would the phase angle be. So for this, what we do is it'd be 0.5 is the overall intensity is equal to cosine squared theta. So then what we'd have to do here is square root both sides, so we get 0.5 is equal to cosine theta. And then when we take the inverse tangent, or inverse cosine, we can find the answer to this, which I'll plug into my calculator real quick, and I'll be back with the answer. What we end up getting is 45 degrees as the answer to this question, which makes sense. And from here, I think we're going to move on to a more medical application of optics, and this will have to do with your actual human eye and a couple of possible conditions that are very prevalent in society and everything around us. So, thank you, and stay tuned for part 2 of the project. Thank you.